All right, it's time for us to get a little bit more into chemical calculations. In this video, we're going to talk about formulas and percent compositions, where, at least for this video, we mean percent by mass when we talk about that, okay? Given a chemical formula, it's pretty easy to find out what fraction of the mass would come from each element, okay? You can do that because you could add up the total molar mass for the compound. We've already talked about how to do that, right? And along the way, as you find that total molar mass, you're finding the mass of each element that would be in the compound, right? So if you divide the part that is one element divided by the total, you'll get the total molar mass, right? That's just how we find percentages, right? So the molecule we've worked with in the last couple of videos, we've had the formula C12H12O4, okay? When we talked about molar mass, I believe we calculated the molar mass of that substance to be about 220 grams per mole. Out of those 220 grams per mole, there are 12 carbons, it says there in the beginning. So 12 times 12 grams per mole for carbon, that means I'd have 144 grams of carbon for every 220 grams of the whole compound. If I divided those two numbers and turned that into a percentage, that would be the percentage of the mass that came from carbon. That's what a mass percentage is, okay? That's a pretty easy calculation. If you want to do it just to check up on yourself, when I did the numbers for that particular formula, I got what's on the bottom of the screen there, about 65% carbon, 5.5% hydrogen, 29% oxygen is what I got when I did that calculation. So hopefully those are the correct numbers. Most of the time in this video is going to be spent on doing the reverse of that calculation. Which means we're going to start with knowledge of the percentages, the mass percentages, and see how we can go about finding a formula from them, right? This is a little bit more difficult process. I'm not going to lie about that. I won't call it a super hard problem because it mostly just follows a pattern, okay? This happens a lot in people that analyze unknown substances. If you worked in a forensics lab, this is the sort of thing you might do pretty regularly, where you get a sample of something and your job is to find out what compound it might be. One of the first steps you might take would be to take some of your sample and inject it into an instrument that does what's called elemental analysis. That's a fancy way of saying it figures out those mass percentages for us, okay? If you get those percentages, you have to be able to convert those into a formula. It should make sense that that would work because either knowing in the formula, our formulas are telling us what's in the molecule in terms of numbers of atoms, which is like being in numbers of moles, okay? So in that formula from the previous slide there, the C12H12O4, if I had 1 mole of that compound, I would have 12 moles of carbon in it, right? And 12 moles of hydrogen in it, and 4 moles of oxygen in it, right? And so that's the composition in terms of numbers of moles or numbers of atoms. If I wanted to change that into masses, I would just use the atomic weights of the elements, right? So they have the same information content or knowledge value one way or the other. We should be able to do the conversion between them. So this is going to be a video where I'm just going to do examples for the rest of the time. Basically, I'm going to do this example twice, once using all the information that's there and once pretending that I've lost some of my information, okay? So I've got my percentages there. It says the molecule I'm going to work with for some reason is nicotine, just a randomly chosen molecule, really. And it says it's 74% carbon, 8.7% hydrogens, and 17.3% nitrogen. That's by mass, okay? It also says we know the molar mass is 162.24. So if we were in a lab analyzing this, that means we also took a little bit of our sample and injected it into a mass spectrometer maybe and got its molar mass. And our task is to find the chemical formula. Okay, so those are all my numbers up there. And here's what I'm going to do. I want to turn those percentages, from percentages, I want to turn them into masses. And then from masses, I want to turn them into moles, because I have my information right now in terms of what fraction of the mass comes from carbon. I want to know what portion of the atoms come from carbon, right? So I have to pick a sample size to get my percentages made into masses. Because I know this molar mass up here, by far the simplest mass I can choose is 1 mole. So I'm going to choose that molar mass, 162.24 grams. I'm going to say that's the size sample I want to start off with. Okay, if I had 162.24 grams of my compound, I know that 74% of those would be carbon, right? So I'm going to turn my 74% from here. That's just going to come and be my 0.74. Multiply those numbers, and I have notes beside me that says I have 120.06 grams of carbon in 1 mole of nicotine. Okay, do the same thing for the other elements because I want to know them all. So I'm going to again take my 162.24 gram sample. I'm going to multiply by the fraction for that one, which is now 0.087. Multiply that out, and my notes tell me I should get 14.11 grams of hydrogen. Still starting with my 1 mole sample. 17.3%, which will be 0.173. Multiply that one out, and I get 28.07 grams of nitrogen. And all of those masses are how much is in 1 mole of nicotine. All right, so here's where we get to see why it was convenient to know the molar mass and to start with that sample. Because I took 1 mole of the compound, those masses need to correspond to a whole number of moles of each of the elements, okay? So all I'm gonna do is take these masses and convert them to moles. So that says I take my 120.06 grams of carbon, I divide them by, if I look in the periodic table, it tells me 12.011 grams of carbon per mole. Divide that out, and I get something that my notes tell me is 9.995, which I'm willing to call 10 moles of carbon. Okay, do the same thing, and I do my 14.11 grams of hydrogen. I'm going to divide that by 1.008 grams of hydrogen per mole. I'll get 13.998, which we're going to call 14 moles there of hydrogen. And for the nitrogen, I've got this one. So I'm going to take my 28.07 grams and divide that by the nitrogen molar mass, which is 14.007 grams per mole. That gives me 2.004, my notes say, which we're going to call 2. You'll notice that when I did this problem for really about the first time, I put all these decimal places in my molar masses. This is an example of a place where I like to do that. I like to do that because when I get to the results here, my numbers of moles, I expect them to be whole numbers. And if I use all the accuracy I can, then when I get the numbers, they should be really, really close. So although I'm doing a little bit of rounding here, you can see I'm rounding 0.995 and 0.998. I'm not rounding 0.87 or something like that and taking it up to be 1, okay? If I get a number that's not really close to being an integer when I do this, then I'll decide I probably did something wrong. So that tells me my formula looks like it's C10H14 N2. Right, so that should be the formula for my nicotine molecule based on what we did there. Okay, that's a sort of standard process calculation. It is made simpler, as we'll see in a moment, by the fact that we started off knowing the molar mass. Okay, I'll tell you in a moment. We're going to do this calculation again, where we pretend that we did not know the molar mass, and we'll see how we can get a result still from that. Just in case you want some more practice doing the line structures, I put in here a picture which is the structure of a nicotine molecule, okay? So if you take that structure and fill in your atoms, you should be able to round that out to be C10H14 and obviously N2, because we can see the 2 N's written down there, okay? Now notice that I could not tell that was what the molecule looked like just from that formula, right? From my percentages, I can't say it's definitely nicotine. I can just say it's got that formula. There could easily be some other compounds that would have a different looking structure that had the same numbers of atoms in there, okay? Because there's likely more than one way I could hook up those atoms to make a molecule. All right, same problem, take 2. You'll notice that this time I have grayed out the part that said I knew the molar mass, all right? So now I'm gonna do the problem starting off without knowing the molar mass. Okay, and that's going to mean I'm not going to just magically say I'm picking 162 grams to be my sample size, right? Because no one would do that. So this is now my starting information. What I'm going to do here is I still want to turn my percentages into masses. So since I don't know what is a mole, I'm going to have to pick a random amount to work with. I'm going to pick 100 grams. okay? Because a 100-gram sample is going to make it easy to turn those percentages into masses at least, okay? So in 100 grams, I will have 74 grams of carbon. I will have 8.7 grams of hydrogen, and I will have 17.3 grams of nitrogen, okay? I want to turn those things into moles. So for the carbon, this says I have 1 mole of carbon is 12.011. And again, this is a problem I definitely want to do with all of my, my decimal places that I can get for my atomic weights. This is one of the very few problems in the early part of this class where it is beneficial to be doing that. These are the hydrogens, so that's 1.008 grams. My nitrogens, a mole of nitrogen is 14.007 grams. Okay, and if you were doing this problem, you'd be probably having to go and look those numbers up if you wanted to get the decimal places at least, okay? I have 2 advantages. One is I have a paper sitting next to me over here that just has the information written on it, so I can look down there and get them. The other thing I have going for me is I've literally been teaching this course for the last 30 years, and so sadly, I kind of know the molar masses of the first fairly large number of elements in the periodic table because I just do this kind of thing a lot, okay? I certainly don't expect you to just remember all those numbers. When I multiply those out, I get 6.161 up here, I get 8.631, and I get 1.235. Notice those numbers are not particularly close to being whole numbers, okay? I definitely do not want to just take those and round them to be whole numbers, okay? Because they're not whole numbers, just look at them, right? And there's no reason why they should be, because now my starting amount, instead of being a mole like it was last time, my starting amount now is just a randomly chosen 100 grams. There's no reason in the world why there needs to be a whole number of moles of carbon in 100 grams of anything that I just scoop up, okay? So right now, this is how many moles I have in 100 grams, okay? So these numbers are moles in 100 grams of nicotine, moles of each element in 100 grams of nicotine. Okay, so what are we going to do about this? We have that set of numbers. We want to convert them into numbers that still have the same ratio among them as those do, right? Because those are based on the right percentages. We just want to get them to be whole numbers, okay? The easiest route to get to whole numbers is to start off by taking the numbers we've got right now. Anything I do to any one of those numbers, I have to do it to all of them. But what I'm going to do is divide them by the smallest number. Okay, why am I going to do that? Because if I divide the smallest one by itself, it's going to turn into 1. Okay, if I'm lucky, then the other ones are also going to turn into whole numbers. Okay, so in this case, my smallest number is this one. So I'm going to take them all and divide them by 1.235. When I do that, this one very obviously becomes equal to 1. Okay, my other ones here, this becomes, my notes tell me 4.989. This one becomes 6.989 by something of a coincidence. Okay, those numbers, I'm now willing to say those are pretty much whole numbers, right? So I'm going to take those and I'm going to say this is 5 and this is 7. All right, suppose they were still not really close to being whole numbers. If that's the case, and you could see an issue like that because there's no rule that says every molecule has to have a 1 of something in its formula, okay? And so if they were not whole numbers now, what I would have to do is I would have to take them and I would have to make them into whole numbers by doing something to all of them, okay? In other words, if I got right now, instead of having 4.989, suppose I had something that was 2.5 there, right? Or it was 2.499 or something like that. If they're not whole numbers at that stage, when I get to here, then most likely what's going to happen is that there'll be fractions you can recognize, something 0.5 or something 0.33. Right? If I had one that was 2.5, I'd say, well, they'd be whole numbers if I multiplied by 2. I'd still have to multiply them all by 2, right? Because I can't change one of those numbers without changing them all. Now let's talk about the formula we got, because if I take that and make it into a formula, what I've got is C5H7N. Okay. Sadly, my iPad just disconnected, so I can't easily write on here. I guess just for sport, I will try to write that with a mouse and say it says C5 H7N. That was actually surprisingly not bad for writing with the mouse. Notice that this formula is very much not what we got before, okay? So that should trouble us a little bit. We got two different formulas, all right? And so let's talk about why that is to wrap ourselves up here. What we have there are, we have the two different kinds of formulas. The one I just found, the C5H7N, that's what's known as the empirical formula. It has the right ratio of atoms, but it doesn't know how big the molecule is, okay? The first one we got, the C10H14 N2, that one is the molecular formula. That one actually knows how big a molecule is, okay? What was the difference in information we started with? It was the molar mass, okay? So there could be lots of different molecules that have the same ratio, right? In chapter 2, where it talks about polyethylene, for example, what polyethylene really is an enormously long chain of CH2 pieces, okay? So if I measured the empirical formula of that polyethylene, it's pretty much CH2, right? If I actually had a molecular formula, it's going to have thousands and thousands of atoms of each kind in there, right? Because the molecules are super long. So that's the difference between the two things. If you want to be able to get a molecular formula, you need to know not only the percentages, but you need to know at least a little bit about the molar mass, okay? Suppose, for the sake of argument, that I was doing this one, and maybe I didn't know that the molar mass was whatever we said, 162.24, right? But maybe I knew the molar mass was between 100 and 200. Okay, that would actually still work out for me in this case to let me say that I needed two of them. Why is that? Because if I took the molar mass of my C5H7N here, I would get a value of about 81. Okay, so I would say that's not big enough to be between 100 and 200. I would need to have a multiple of that, right? Because the other way to do this is say my real molecular formula is kind of this formula, and sometimes people actually take this and write it like this and put an N or an X or something down there to say it's got to be a whole number multiple of that, okay? So I won't get the empirical formula and multiply it by a fraction. It would always be a whole number. In this case, there are two of those empirical formulas that make up the molecular formula for the case of our nicotine compound that we've been working with.